January 21st, 1941. Freeport, Texas. Steam hissed from massive processing tanks as Gulf of Mexico seawater flowed through miles of pipes at the world's most ambitious chemical experiment. German engineering experts had been clear since 1886. Extracting magnesium from seawater was a chemist's fantasy. Solid mineral ores were the only viable source. Period. Yet here, against the roar of electrolytic cells and the hiss of molten metal, American engineers poured the first ingot of seawater magnesium in human history. 99.8% pure, silvery, perfect. Today, 83 years later, that impossible metal still serves in aircraft museums worldwide, while modern magnesium corrodes and fails within months of exposure. The same element, the same chemical formula. But somehow, what American engineers achieved in 1941 defied not just European expertise, but the laws of materials science itself. How did Depression-era chemistry create magnesium more durable than anything we produce today? Since 1886, the world's magnesium had flowed from the same proven source, solid earth. German engineers had perfected the process in their electrolytic facilities, processing magnesite and dolomite from carefully selected mineral deposits across Europe. The chemistry was settled science. The infrastructure was established. The economics were proven. Every ton of the silvery metal that strengthened aircraft frames and lightened automotive components traced back to rocks pulled from mines, crushed in mills, and processed in massive industrial complexes that represented 50 years of accumulated engineering wisdom. Herbert Dow had dreamed differently since 1924. Standing on a Michigan shoreline, watching endless waves roll toward the chemical plants that had made his fortune, he envisioned something no European engineer considered possible: mining the ocean itself. The math seemed obvious to him. If his underground brine wells could yield magnesium through electrolytic processing, why couldn't seawater? The Great Lakes contained more dissolved magnesium than all the world's known ore deposits combined. The Atlantic Ocean held enough to supply global demand for millennia. But Herbert Dow died in 1930, his ocean mining vision existing only in scattered notes and the determined memory of his son. Willard Dow inherited both the chemical empire and the impossible idea. Through the depths of the Great Depression, while competitors shuttered plants and laid off workers, he quietly funded research into seawater processing. The breakthrough came in 1939 at Curay Beach, North Carolina, where Dow engineers perfected the extraction of bromine from Atlantic seawater. The operation processed 6 cubic miles of ocean water annually, producing 2.4 billion pounds of bromine with startling efficiency. The chemistry worked. The economics worked. The scale was breathtaking. But magnesium presented challenges that made bromine extraction look simple. Each ton of magnesium required processing 800 tons of seawater through a complex series of chemical transformations. The seawater had to be mixed with lime to precipitate magnesium hydroxide, which then required conversion to magnesium chloride before final electrolytic processing could yield pure metal. The volume calculations were staggering. A commercial-scale plant would need to process millions of gallons of seawater daily, requiring infrastructure that had never been built anywhere in the world. As war clouds gathered over Europe in late 1939, Dow's board faced a critical decision about location. The Gulf Coast offered advantages the Atlantic couldn't match: year-round warm weather, abundant natural gas for power generation, and proximity to oyster shell deposits that could provide the limestone necessary for processing. 2 Texas sites emerged as possibilities: Corpus Christi and Freeport. The board scheduled a January 1940 site inspection to make their final choice. Mother Nature made the decision for them. A freak ice storm struck Corpus Christi during their visit, coating the industrial waterfront in sheets of ice that made construction assessment impossible. The board members, shivering in overcoats as they surveyed the frozen harbor, unanimously voted to head south to Freeport. There, under clear Texas skies, they found 800 acres of marshland at Freeport Harbor, with direct access to the Gulf of Mexico, natural gas pipelines, and the Brazos River freshwater that would be essential for the final processing stages. Dr. Alfred P. Beutel stepped into this complexity with the confidence of a man who had never met an engineering challenge he couldn't solve through sheer force of will and systematic execution. Hard-driving and results-obsessed, Dutch Beutel had earned his reputation by completing projects others deemed impossible, always ahead of schedule and under budget. When Willard Dow named him head of the new Texas division, Beutel surveyed the Freeport site with the eye of a general planning a campaign. The resources aligned perfectly: unlimited Gulf seawater, abundant natural gas from nearby fields, massive oyster shell deposits for lime production, and Brazos River freshwater for the final electrolytic cells. On March 7, 1940, Dow Chemical purchased 800 acres at Freeport Harbor. Construction crews arrived within weeks, but the engineering reality struck with sobering force. The process required heating oyster shells to temperatures exceeding 2,000 degrees Fahrenheit to produce calcium oxide. This lime would then be mixed with incoming seawater in massive agitated flocculators to precipitate magnesium hydroxide. The hydroxide would settle in door thickeners before conversion to magnesium chloride through hydrochloric acid treatment. Finally, the chloride would undergo electrolysis in cells consuming enormous amounts of electrical power to yield pure magnesium metal. Each step demanded precision engineering at unprecedented scale. The intake system alone required pumping millions of gallons of corrosive seawater daily through miles of specially designed piping. The lime plant needed infrastructure capable of processing trainloads of oyster shells every day. The electrolytic cells would consume more electricity than entire cities, requiring dedicated power generation facilities. No one had ever attempted magnesium extraction from seawater at industrial scale. European experts remained convinced it couldn't work economically. By December 1940, 8 months into construction, even Dow's most optimistic supporters began questioning whether they had bet the company's future on a beautiful impossibility. The German magnesium plants that supplied global demand had been perfected over decades of incremental improvement. The chemistry was proven. The economics were established. The infrastructure existed. Against this accumulated wisdom stood 800 acres of Texas marshland, construction crews working around the clock, and Dutch Beutel's unwavering certainty that American engineering could accomplish what European expertise deemed impossible. The first test would come in January. 8 months to prove that the ocean could yield its metallic treasures as reliably as any terrestrial mine. Under Dutch Beutel's legendary drive, construction moved with wartime urgency even before America entered the war. The chlorine caustic plant rose first in December 1940, its towering electrolytic cells designed to split seawater into its component chemicals. Massive concrete foundations anchored equipment that would operate under conditions no previous industrial facility had attempted. The caustic soda produced would neutralize the hydrochloric acid needed for magnesium chloride conversion, creating a closed-loop system that minimized waste and maximized efficiency. Construction crews worked in rotating shifts around the clock, their welding torches illuminating the Texas marshland through the night. The magnesium extraction plant followed immediately, its design incorporating lessons learned from the Cure Beach bromine facility, but scaled beyond anything previously imagined. Where the North Carolina plant processed thousands of gallons of seawater daily, Freeport would handle millions. The intake apparatus alone required engineering innovations that pushed the boundaries of materials science, as seawater's corrosive properties would destroy conventional piping within months. The lime plant presented its own set of engineering challenges. Trainloads of oyster shells arrived daily from Gulf Coast harvesting operations, their calcium carbonate content essential for the chemical precipitation process. The shells required heating to 2,100 degrees Fahrenheit in specially designed kilns that consumed enormous quantities of natural gas. The resulting calcium oxide, or quicklime, would then be transported through enclosed conveyor systems to prevent contamination while maintaining the purity levels essential for magnesium extraction. Millions of gallons of Gulf seawater flowed daily through the intake apparatus, a marvel of corrosion-resistant engineering that channeled the ocean's bounty into the heart of American industrial chemistry. The seawater moved through primary screening to remove debris, then into massive mixing chambers where it encountered the freshly produced lime. The chemical reaction was immediate and dramatic. Calcium hydroxide combined with dissolved magnesium sulfate to precipitate magnesium hydroxide in clouds of white crystals that transformed the clear seawater into a milky suspension. The precipitation process required precise control of temperature, pH, and mixing intensity. Massive agitated flocculators, each the size of a small building, provided the turbulent environment necessary for optimal crystal formation. The magnesium hydroxide particles had to grow large enough for efficient separation, but remained small enough for complete chemical conversion in later stages. Engineers monitored the process continuously, adjusting lime addition rates and mixing speeds to maintain the delicate chemical balance that determined the entire operation's success. From the flocculators, the magnesium-rich slurry flowed into door thickeners that separated the precipitated hydroxide from the processed seawater. These circular settling tanks, each over 100 feet in diameter, used carefully controlled overflow rates to concentrate the magnesium while allowing the depleted seawater to return to the Gulf. The engineering precision required was extraordinary. Too fast a flow rate and valuable magnesium would be lost. Too slow, and the entire process would bottleneck, shutting down production. The concentrated magnesium hydroxide then underwent conversion to magnesium chloride through treatment with hydrochloric acid produced in the adjacent chlorine caustic plant. This neutralization reaction generated enormous amounts of heat that had to be carefully controlled to prevent unwanted side reactions. The resulting magnesium chloride solution, containing over 20% dissolved magnesium, represented the culmination of the chemical pre-processing stages that transformed seawater into a concentrate suitable for electrolytic processing. The final stage required the most advanced technology, electrolytic cells operating at temperatures exceeding 1,300 degrees Fahrenheit. These steel vessels, lined with refractory materials capable of withstanding molten salt conditions, consumed electrical power at rates that staggered even experienced chemical engineers. Each cell required precise control of electrical current, temperature, and chemical composition to ensure efficient magnesium production while preventing the formation of unwanted compounds that could contaminate the final product. The scale was unprecedented in the annals of industrial chemistry. Where European magnesium plants processed tons of solid ore daily, Freeport handled thousands of tons of seawater every hour. The engineering systems operated continuously, their synchronized operation requiring coordination between intake pumping, lime production, chemical precipitation, settling, concentration, and electrolysis stages that had never been attempted at such magnitude. January 21, 1941, marked the culmination of 8 months of construction and engineering that had transformed 800 acres of Texas marshland into the world's most ambitious chemical facility. Steam rose from processing units as operators initiated the final electrolytic sequence. Molten magnesium chloride, heated to temperatures that would melt copper, underwent the electrical transformation that separated magnesium metal from chlorine gas in a process that had been theoretical until this moment. The first ingot emerged as a silvery stream of pure metal, glowing with the heat of its birth from the sea. For the first time in human history, the ocean had yielded its metallic treasures through industrial processing that rivaled nature's own geological forces in complexity and surpassed them in speed. The ingot cooled to reveal magnesium of 99.8% purity, exceeding the quality of metal extracted from the finest terrestrial ores through processes perfected over decades. The achievement represented more than successful chemistry or engineering prowess. American ingenuity had literally mined the ocean, extracting strategic metals from an inexhaustible source that European expertise had dismissed as economically impossible. The silvery ingot cooling in the Texas facility contained magnesium purer than anything produced from mined ores, created through processes that would soon supply the aluminum aircraft and lightweight alloys essential for American air superiority in the global conflict already consuming Europe and Asia. Within 12 months of that first silvery pour, the Freeport plant reached 18,000 tons annual capacity, transforming the Texas Gulf Coast into America's primary source of strategic magnesium. The production numbers staggered even Dow's engineers, who had designed the facility with ambitious targets, but watched their projections exceeded month after month. By late 1941, industrial publications characterized Dow's Texas operation as the #1 defense plant in the nation, its seawater magnesium flowing directly into aircraft factories, where American air power was taking physical form. Pearl Harbor changed everything overnight. The attack on December 7th transformed magnesium from an important industrial metal into a critical war material essential for American survival. Aircraft production demanded unprecedented quantities of lightweight alloys, and magnesium formed the backbone of engine components, structural frames, and landing gear that would carry American pilots into combat across 2 oceans. The government's response was immediate and uncompromising: double capacity within 8 months or risk losing the war in the air. Dutch Boydell received the expansion order with characteristic directness from Washington officials who made clear that failure was not an option. The United States military required enough magnesium to support aircraft production rates that would eclipse anything previously imagined in peacetime. American factories would build planes at rates exceeding 11 per hour at peak production, each aircraft containing magnesium components that European suppliers could never provide in sufficient quantity or quality. The mathematics were stark. Without massive increases in domestic magnesium production, American air superiority would remain a strategic impossibility. Construction began immediately on a second plant at Velasco, just miles from the original Freeport facility. The engineering timeline compressed every lesson learned from the first plant into 8 months of construction that pushed American industrial capability to its absolute limits. Where the original facility had required careful experimentation and gradual scaling, the Velasco plant incorporated proven designs that could be replicated with wartime efficiency. Concrete foundations poured while equipment was still being manufactured in distant factories, creating construction sequences that required unprecedented coordination between suppliers across the American industrial base. The workforce challenge threatened to derail the entire expansion before construction could begin in earnest. Freeport in 1941 remained a small marshland village with fewer than 1,000 residents, lacking infrastructure to support the thousands of workers required for round-the-clock construction and operation of 2 massive chemical plants. Housing, utilities, transportation, food service, and medical facilities needed to materialize from nothing in a location that offered little beyond direct access to Gulf seawater and natural gas pipelines. Buell's solution demonstrated the same systematic thinking that had driven the original plant construction. Rather than rely on existing communities or gradual infrastructure development, he organized Camp Chemical as a complete temporary city designed and built specifically for the magnesium project. The construction timeline was breathtaking even by wartime standards: 31 days to create housing for 12,000 workers in a location that had never supported more than a few hundred residents. 2,000 cottages rose from the marshland in perfect rows, each designed for maximum construction speed while providing decent living conditions for the families that would call Camp Chemical home for the duration of the war. 46 barracks housed 5,520 single men, their dormitory-style accommodations Spartan but functional. Cafeterias capable of serving thousands of meals daily operated around the clock to support construction crews and plant operators working rotating shifts. Schools appeared for the children of families drawn to Texas by wages that made chemical plant work more attractive than anything available in Depression-era America. Recreation facilities provided essential relief from the intensity of wartime construction schedules. Movie theaters, sports fields, and social clubs created community life in a location that had been empty marshland months earlier. At its peak, Camp Chemical housed 12,000 people, making it the largest city in Brazoria County and one of the most remarkable examples of planned community development in American industrial history. While Camp Chemical provided immediate housing solutions, Willard Dow recognized that temporary wartime facilities could not support the long-term workforce needed for sustained magnesium production. Along with his architect brother Alden and Dutch Boydell, he scouted the surrounding countryside on horseback, seeking a location for a permanent town that could house 5,000 residents in conditions worthy of the families building America's chemical future. They selected the former Abner Jackson Plantation, 8 miles inland from the Gulf Coast, and positioned on higher ground that provided protection from the hurricanes that periodically devastated coastal Texas. The site offered natural drainage, access to fresh water, and enough elevation to ensure that storm surges could never threaten the community. Alden Dow approached the town planning with the same systematic precision he brought to architectural design, creating winding streets that followed the natural contours of the land, rather than imposing geometric patterns that ignored local topography. The town of Lake Jackson emerged from Alden Dow's vision of American industrial communities that prioritized human needs alongside production efficiency. 6 distinct house designs provided variety while maintaining construction efficiency, their architectural details reflecting contemporary American residential design, rather than the utilitarian barracks that characterized many wartime industrial communities. Streets curved with something of a surprise around each turn, creating neighborhoods that felt organic rather than institutional. By 1942, Dow's 2 seawater plants had combined capacity of 92,000 short tons annually, providing 84% of America's total magnesium output from facilities that had not existed 3 years earlier. The engineering achievement represented more than successful chemistry or construction management. American ingenuity had created an entirely new industry from theoretical concepts, transforming empty marshland into the foundation of national defense while building communities that would outlast the war itself. 1942 marked the critical test of whether American seawater magnesium could sustain the industrial demands of global warfare. Aircraft factories across the nation operated at production rates that defied peacetime imagination, their assembly lines producing warplanes at 11 per hour during peak shifts. Every B-17 Flying Fortress, P-51 Mustang, and B-24 Liberator. Rolling off production lines contained magnesium components that traced directly back to the Gulf of Mexico processing plants that had materialized from Texas marshland in less than 2 years. The strategic importance became clear through simple mathematics. American air superiority required aircraft production that exceeded the combined output of German, Japanese, and Italian factories, with each plane containing engine casings, landing gear, and structural components fabricated from magnesium alloys. European magnesium supplies, even if accessible through wartime shipping, could never match the volume flowing from Dow's seawater plants. The 92,000 short tons of annual capacity represented the difference between American industrial might and strategic vulnerability. Quality testing revealed characteristics that surprised even Dow's engineers. The seawater magnesium consistently achieved 99.8% purity through the distillation and vapor deposition processes that separated pure metal from the electrolytic cells. This purity level exceeded anything produced from mined ores, where conventional processing introduced trace impurities that remained embedded in the final product. The Pidgeon process, used extensively for terrestrial magnesium production, operated at temperatures exceeding 1200 degrees Celsius and inevitably introduced zinc, manganese, and silicon impurities that created microscopic contamination sites throughout the metal's crystalline structure. European electrolytic processes, refined over decades of industrial development, still produced magnesium containing chloride residues and various metallic impurities from the original ore sources. These contamination elements, while present in small quantities, created galvanic sites where corrosion could initiate when the metal encountered moisture or salt environments. The chemistry was straightforward. Dissimilar metals in contact with electrolytes created electrical potentials that drove electrochemical reactions, leading to rapid deterioration of the magnesium matrix. Seawater magnesium avoided these contamination pathways entirely through the inherent purity of its source material and processing methods. Ocean water contained dissolved magnesium in ionic form, free from the complex mineral matrices that characterize terrestrial ores. The precipitation and electrolytic processes removed virtually all foreign elements, creating metal with crystalline structures that contained fewer defect sites where corrosion could establish footholds. The distillation conditions required for final purification operated at temperatures and pressures that eliminated trace contaminants through vapor separation techniques unavailable to conventional smelting operations. Aircraft manufacturers reported exceptional performance from components fabricated with Texas magnesium. Engine casings maintained dimensional stability under extreme temperature cycling that caused failures in parts made from conventional magnesium alloys. Landing gear assemblies showed remarkable resistance to the galvanic corrosion that typically developed where magnesium contacted aluminum or steel components in the presence of moisture. Structural frames retained their strength characteristics through stress cycles that exceeded design specifications, providing safety margins that proved critical in combat conditions. The production achievement represented more than successful chemistry. American engineers had created magnesium that surpassed European metallurgical standards through processes that utilized an inexhaustible resource base. Where German facilities depended on finite ore deposits that required increasingly expensive extraction as higher-grade materials became depleted, Dow's plants drew from Gulf waters that contained magnesium concentrations maintained by global oceanic circulation patterns spanning geological timescales. Economic analysis revealed the strategic implications. European magnesium cost structures reflected the cumulative expenses of mining, ore transportation, complex smelting operations, and the infrastructure investments required to maintain supply chains across multiple countries. American seawater processing eliminated mining costs entirely, reduced transportation expenses to the movement of finished metal rather than raw materials, and concentrated all production activities at facilities positioned for optimal resource access and distribution efficiency. The workforce that sustained this production miracle numbered in the thousands, their efforts coordinated through management systems that Dutch Beudel had refined into models of industrial efficiency. 3 shifts operated continuously, their personnel rotations timed to maintain optimal production rates while providing the safety margins essential when working with molten metals and corrosive chemicals. Training programs developed specifically for seawater magnesium production created expertise that existed nowhere else in the world, as no other facilities had ever attempted metal extraction from ocean resources at industrial scale. Success bred new challenges that would ultimately test the durability of the entire enterprise. The economics that made seawater magnesium competitive during wartime reflected specific conditions that might not persist in peacetime markets. Power costs, labor expenses, and raw material availability could shift dramatically when military demand ended and commercial markets resumed normal competitive dynamics. European producers, temporarily disrupted by wartime conditions, retained decades of experience and established customer relationships that American facilities would need to match through superior performance rather than strategic necessity. By late 1942, however, such concerns remained theoretical. The immediate reality was American air superiority built on magnesium extracted from the sea through engineering processes that had transformed theoretical chemistry into strategic capability. Every squadron of bombers crossing the Atlantic toward European targets carried components fabricated from metal that had been dissolved in Gulf waters months earlier, their exceptional purity ensuring performance reliability under combat conditions that would destroy inferior materials. The test continued daily through production runs that supplied the arsenal of democracy with materials no other nation could match in quantity, quality, or strategic security. American seawater magnesium had proven itself under the most demanding conditions imaginable, total war against industrial adversaries whose own metallurgical expertise represented centuries of accumulated knowledge and development. Decades passed before the full magnitude of Dow's achievement became apparent through discoveries that defied modern materials, science expectations. Aircraft mechanics restoring Cold War-era bombers in the 1990s began reporting something extraordinary. Magnesium components from B-36 and B-47 aircraft showed exceptional longevity after 50-plus years of service, far exceeding contemporary predictions for magnesium alloy durability. Structural frames, engine mounting brackets, and landing gear assemblies fabricated during the war years retained their integrity with minimal corrosion damage, even after decades of exposure to moisture, temperature cycling, and operational stresses. The Federal Aviation Administration's metallurgical laboratories confirmed what restoration specialists had observed in hangars across America. Magnesium parts manufactured between 1941 and 1945 exhibited corrosion resistance characteristics that contradicted established knowledge about magnesium behavior in service environments. Modern materials. Science textbooks described magnesium as inherently prone to galvanic corrosion, requiring extensive protective coatings and careful design to prevent rapid deterioration. Yet wartime components continued functioning with surface conditions that suggested fundamental differences in metallurgical properties. By the 1990s, global magnesium production had shifted dramatically toward Chinese facilities using the Pidgeon process, a thermal reduction technique that processed dolomite with ferrosilicon in sealed retorts heated to 1200 degrees Celsius. This method, developed in Canada during the 1940s, offered lower capital costs and reduced electricity consumption compared to electrolytic processing, making it economically attractive as energy prices rose and labor costs increased in traditional producing countries. Chinese producers, with access to abundant coal for power generation and lower labor expenses, gradually captured global market share through aggressive pricing strategies that undercut Western manufacturers. The Pidgeon process, while economically efficient, introduced metallurgical characteristics that differed substantially from electrolytic magnesium. Thermal reduction inevitably incorporated iron, silicon, and other elements from the ferrosilicon-reducing agent into the final product, creating microscopic inclusion sites throughout the metal's crystalline structure. These foreign particles acted as galvanic cells when the magnesium encountered moisture, initiating corrosion reactions that spread rapidly through the surrounding metal matrix. Modern magnesium showed rapid pitting corrosion and hydrogen evolution in marine environments, requiring extensive protective coating systems that added cost and complexity to manufacturing processes. Power costs at Freeport had risen steadily through the 1980s and 90s as natural gas prices increased and environmental regulations imposed additional operating expenses on chemical facilities. The aging electrolytic cells required major maintenance investments to continue operating at design capacity, while newer technologies offered alternative production methods that promised lower operating costs. Chinese producers offered magnesium at prices that made continued seawater processing economically untenable for commercial markets that prioritized immediate cost savings over long-term performance characteristics. In 1998, after 57 years of continuous seawater magnesium production, Dow Chemical began systematic shutdown of the facilities that had once supplied 84% of America's strategic metal needs. The electrolytic cells fell silent, their molten salt contents cooling for the final time as economic realities forced abandonment of processes that had proven technologically superior but commercially unsustainable. The company exited the magnesium business entirely, focusing resources on petrochemical products that offered better profit margins in increasingly competitive global markets. The knowledge that had enabled ocean mining vanished with the plant closures. Engineers who understood the precise chemical balances required for seawater processing retired without training successors in techniques that seemed economically obsolete. Operating manuals disappeared into corporate archives as facilities were dismantled and sold for scrap metal. The institutional expertise that had transformed Herbert Dow's impossible vision into industrial reality became historical footnote rather than active technological capability. Materials scientists studying the durability differences began uncovering the metallurgical explanations behind the performance gap. Electrolytic seawater magnesium achieves superior corrosion resistance because the processing conditions inherently removed impurities that created galvanic sites in conventionally produced metal. The distillation and vapor deposition techniques used in the final purification stages operated under controlled atmospheres that prevented contamination from atmospheric gases or processing equipment. Ocean source purity meant the raw material contained dissolved magnesium free from the complex mineral matrices that characterized terrestrial ores. The crystalline structure of seawater magnesium contained fewer lattice defects where corrosion reactions could initiate and propagate. Modern scanning electron microscopy revealed grain boundaries and inclusion patterns that differed significantly from thermally reduced magnesium, with the electrolytic metal showing more uniform microstructures and reduced chemical heterogeneity. These microscopic differences translated into macroscopic performance advantages that became apparent only through decades of service experience. Aircraft museums worldwide displayed the evidence of American metallurgical achievement in components that continued serving their intended functions 80 years after manufacture. Engine mounts from P-51 Mustangs retained structural integrity with surface patina that indicated minimal corrosion progression. Landing gear assemblies from B-24 Liberators showed wear patterns consistent with normal mechanical loading, rather than the accelerated deterioration characteristic of galvanic corrosion. Flight control brackets maintained dimensional stability that allowed continued operation in restored aircraft flown regularly at air shows and commemorative events. Modern magnesium components required replacement within months of installation in similar service environments without extensive protective coating systems that added weight and complexity to aircraft design. The contrast highlighted performance capabilities that American engineers had achieved through processing methods that utilized the ocean's inherent chemical purity to create metals superior to anything produced from terrestrial resources. Dow's Texas operations evolved from 800 acres of marshland into the largest integrated chemical manufacturing site in the Western Hemisphere, but the knowledge of producing ultra-pure magnesium from seawater disappeared with economic pressures that prioritized immediate cost savings over long-term strategic capability. The town of Lake Jackson thrived as a permanent community, its winding streets and varied architecture testament to planning that considered human needs alongside industrial requirements. Yet the revolutionary engineering that had once supplied America's strategic metal needs from an inexhaustible oceanic resource became lost knowledge, sacrificed to global economics that valued cheap production over metallurgical excellence.